Welcome. Let's take a look at evaluating the integral from 0 to pi over 4 of tangent x over 2 times secant squared of x over 2 dx. I'm going to take just a moment to rewrite this to illustrate a point. And the way I'm going to rewrite this is I'm going to split apart that secant squared, and I'm going to rewrite this as secant of x over 2 times tangent of x over 2 times secant of x over 2 dx. Now, regardless of which way I look at this definite integral, it's not completely obvious what the antiderivative is. And so we're going to want to use some substitution to help us determine the value of this definite integral. In this first case, I can see a tangent of x over 2. And if I think about taking the tangent of x over 2, its derivative would be secant squared of x over 2 times the derivative of x over 2. And so when I look at that integrand, I can see where one component of the integrand is related to the derivative of another component, sans a constant, but we can always deal with constants by multiplying by a cleverly formed number 1. Now, if I look at the second representation I have here on the right, where I have secant of x times tangent secant, notice that if I take the derivative of secant x over 2, that's going to be secant x over 2 times tangent x over 2 times the derivative of x over 2, which is a constant. And so if I wanted to do a substitution, I could choose u to be secant of x over 2. But for our purposes, we're going to go with the more obvious choice here. That is the tangent of x over 2 to do our substitution. So we're going to say let u equal tangent of x over 2. Then du equals the derivative of tangent of x over 2, so secant squared x over 2 times the derivative of x over 2, so I'm just going to write that as x over 2 prime dx. Or we could say du equals secant squared of x over 2, and then my derivative here of x over 2 is going to be 1/2, and so I'm going to multiply by 1/2. I'm going to move that derivative to the front of the function, dx. And so when I look at my integral over here, I'm going to want to have a factor of 1/2, and so I'm going to multiply by 2 times 1/2 being 1, and I haven't really changed the value of my integral. So I'm going to rewrite this as 2 times the integral from 0 to pi over 4 of tangent of x over 2 times 1/2 secant squared x over 2 dx. So what I can see here is now I'm going to be substituting for tangent of x over 2, that's going to become a u, and my 1/2 secant squared dx, that's going to become du. So I'm going to have something that looks like 2 times the integral of u du, but we still need to figure out what those new limits of integration are. So if, let's look at our upper limit, if x equals pi over 4, then u equals tangent of pi over 4 over 2, or more simply, tangent of pi over 8. If x equals 0, then u equals tangent of 0 over 2, which is tangent of 0, and tangent of 0 is 0. So 0 was my lower limit of integration, and when I do my transformation, my x equals 0 becomes u equals 0. So this is still a 0. And my x equals pi over 4 transforms and becomes a tangent of pi over 8. So tangent pi 8ths. And now we have a rather simple definite integral to evaluate. I'm actually going to move that 2 inside our integrand, write that as 2u from 0 to tangent pi over 8 du. Now you might be wondering, why did I move that 2? Well, the reason I moved that 2, and let me write it over here as the side, the reason I did that is I recognized that if I took the derivative with respect to u of u squared, I would get 2u, which means the antiderivative of 2u would be u squared plus a constant. So I just recognized that if I move that constant of 2 inside the integral, I had a basic derivative, and I could just directly find the antiderivative. That is, this would be u squared from u equals 0 to u equals tangent of pi over 8. Well, if I evaluate this, I'm going to get tangent of pi over 8 squared minus 0 squared. So the value of this integral is tangent squared of pi over 8. I hope you find this helpful.